Tonight, we're going to go somewhere no human being has ever been, and no human being could ever survive. Inside a neutron star, a place where the laws of physics stop applying in any familiar way, where the matter that makes up everything you've ever touched, every atom of your body, every rock, every ocean, every planet has been crushed out of existence and replaced by something that has no name in ordinary language. And here's what's going to change the way you see the entire universe. The stuff inside a neutron star isn't just dense. It isn't just compressed. It's matter in a state that only exists in one place in the entire universe, and we are only now beginning to understand what it actually is. By the end of tonight, you're going to understand what's happening inside the most extreme objects in the known universe, and why that understanding might be the key to unlocking some of the deepest secrets in all of physics. Before we begin, if you enjoy these topics as much as we do, make sure to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Pick up a teaspoon. An ordinary kitchen teaspoon, the kind you'd use to stir your coffee. Fill it. That amount of material, if it came from the core of a neutron star, would weigh roughly 5.5 billion metric tons. The weight of roughly 55,000 of the largest aircraft carriers ever built, crammed into a space you could hold in the palm of your hand. Drop it, and it doesn't stop at your palm. Your palm would not survive the encounter. The floor beneath you would not survive. The building you're in, the foundations, the bedrock, the mantle, the entire planet, none of it would survive. It would pass through our entire planet as though it weren't there. Because, from the perspective of something that dense, our planet basically isn't. That's the starting point. That's the thing you need to hold in your head before we go any further. A neutron star is not a star in any sense you'd normally mean. It doesn't burn. It doesn't fuse anything anymore. It's what's left after a star vastly more massive than our sun runs out of fuel, collapses in a fraction of a second, and bounces back in the most violent explosion the universe produces. And what remains the core is something unlike anything else that exists. To understand what's inside, you have to understand how a neutron star is born. And to understand that, you need to start with what an ordinary atom actually is. An atom is mostly empty space. This is a fact that most people have heard, but very few people have actually let sink in. If you took a hydrogen atom, the simplest atom there is, one proton, one electron, and scaled the proton up to the size of a marble, the electron orbiting it would be approximately 1.5 kilometers away. Everything between the marble and that distant electron is empty. Completely, literally empty. Nothing there. And this is true of every atom in your body, in this planet, in every star, in every galaxy. Matter, as we experience it, is almost entirely nothing. The reason it feels solid, the reason it has substance and weight and resistance, is because of electromagnetic forces between electrons. The electrons in the atoms of your hand repel the electrons in the atoms of whatever you're touching. You're not actually in contact with anything. You're being repelled. Solidity is an electromagnetic illusion, a convenient fiction that the universe maintains at low pressures and low densities. When you increase the pressure enough, when you pile enough mass on top of something, the fiction starts to break down. The electrons and nuclei that were separated by vast relative distances start getting pushed closer together. And eventually, you cross a threshold. The threshold where matter as we know it stops existing. In the core of a large star, something between 8 and roughly 25 times the mass of our sun fusion has been running for millions of years. hydrogen fusing into helium, helium fusing into carbon, carbon, oxygen, neon, magnesium, silicon. Each heavier element burning in shells nested around the core like layers of an onion. Each stage runs faster than the previous one. Hydrogen fusion takes millions of years. Helium fusion takes hundreds of thousands. Silicon fusion takes about a day. When the core becomes pure iron, the process stops. Iron is the end of the road for stellar nucleosynthesis. You cannot release energy by fusing iron into anything heavier. Fusing iron consumes energy rather than producing it. So, when the iron core forms, the outward pressure generated by fusion disappears. Gravity wins. And when gravity wins, it wins completely. The collapse of the iron core happens in less than a second. A core the size of Earth, containing between 1 and 2 times the mass of the Sun, collapses to a sphere roughly 20 kilometers across, in a time shorter than a single heartbeat. Think about what that means physically. The entire mass of more than a sun, compressed from an Earth-sized ball into a sphere the size of a city, in under a second. The density shoots up so catastrophically that even the physics of the process is difficult to describe without the mathematics becoming extreme. As the core collapses, the electrons that in ordinary matter orbit the nucleus at enormous relative distances are squeezed directly into protons. The electromagnetic barriers that normally keep electrons and protons apart as separate particles are simply overridden by gravity. When an electron combines with a proton, you get a neutron and a neutrino. The neutrino flies away at nearly the speed of light, carrying energy. The neutron stays. Tens of billions of these reactions happen simultaneously across the collapsing core. The protons and electrons that made up all the atoms in the core are annihilated as separate particles. In their place, a sea of neutrons, packed together so tightly they are essentially touching. Nuclear density. The same density as the nucleus of an atom, but stretched across a sphere 20 kilometers wide. That's what a neutron star is. Not a star of neutrons, in some metaphorical sense. Literally, a sphere of nuclear matter, 20 kilometers across, containing more mass than the Sun. And it forms in under a second. There is no slower way to make one. The process isn't gradual. It doesn't build up. It doesn't take a millennium, or a year, or an hour. In the time it takes you to blink, an iron core the size of our planet has become a ball of nuclear matter the size of a city. That transition, that violence, is what allows everything that follows. The outer layers of the original star, still falling inward when the core hits this density and stops collapsing, smash into the suddenly rigid neutron star surface. They bounce. A shockwave tears outward through the infalling material at a significant fraction of the speed of light. The energetics of this shockwave are staggering. A typical core collapse supernova releases approximately 10 to the power of 44 joules of energy in the form of neutrinos alone. That is more energy than the Sun will radiate across its entire 10 billion year lifetime, released in a matter of seconds. The visible explosion, the supernova itself, which can briefly outshine an entire galaxy of hundreds of billions of stars, accounts for only around 1% of the total energy budget. 99% goes into neutrinos. The neutrino burst from a supernova is so intense that several kilometers of lead wouldn't stop it. In February 1987, a star went supernova in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, roughly 160,000 light-years away. The event, called supernova 1987A, gave astronomers a historic opportunity. Neutrino detectors in Japan, the United States, and the Soviet Union detected a burst of neutrinos arriving in a span of about 12 seconds, roughly 3 hours before the visible explosion was seen. Just 24 neutrinos across 3 separate detectors. That's all we detected from a star exploding 160,000 light-years away, because neutrinos interact with matter so weakly. But those 24 neutrinos were enough to confirm the basic picture of stellar collapse that theorists had built over decades. The timing of their arrival, the energy spectrum, the duration of the burst, all of it matched the models. 24 particles, confirming that our picture of one of the most violent events in the universe was essentially correct. In the chaos of the shockwave expanding outward through the star's outer layers, elements heavier than iron, gold, platinum, iodine, uranium, strontium are synthesized in fractions of a second by processes that cannot happen anywhere else in the universe. Every atom of gold on Earth was created in an event like this. Every piece of jewelry, every gold bar in every vault, every electronic contact in every smartphone, assembled in the violence of a supernova or a neutron star merger, scattered across hundreds of light-years of space, slowly condensing into a gas cloud, collapsing into a new solar system, accreting onto a planet, waiting billions of years for something with hands to pick it up. The supernova is one of the most violent events the universe produces. But what it leaves behind is stranger. Before neutron stars cool entirely, while they're still radiating heat, they can be observed as bright X-ray sources. A freshly born neutron star has a surface temperature around 1,000,000 degrees. At that temperature, the surface radiates primarily in X-rays. In isolated neutron stars, this X-ray emission gradually fades as the star cools over thousands of years. But neutron stars in binary systems orbiting a companion star can remain X-ray bright for much longer. If the companion is close enough and the neutron star's gravity is strong enough, material flows from the companion onto the neutron star. This accreted material falls from the companion's surface, gaining kinetic energy as it falls into the neutron star's deep gravitational well, and releases that energy as X-rays when it hits the neutron star surface. X-ray binaries are among the brightest individual objects in the X-ray sky. Some of them are visible to X-ray telescopes in nearby galaxies. The X-ray emission from these systems carries information about the neutron star in several ways. The luminosity tells you the accretion rate. The spectrum tells you the surface temperature and the gravitational redshift. The timing of X-ray bursts' sudden brightenings caused by thermonuclear burning of accumulated hydrogen and helium on the surface tells you the rotation rate and the composition of the Brupa, accreted material. Some X-ray binaries show quasi-periodic oscillations, rapid flickering in their X-ray brightness at frequencies of hundreds to over 1,000 Hz. These kilohertz quasi-periodic oscillations are thought to reflect orbital motion close to the neutron star's surface, potentially at the innermost stable circular orbit, the closest orbit that's stable against the neutron star's gravity. The radius of the innermost stable circular orbit depends on the mass of the neutron star. Measuring it gives another constraint on the equation of state. Every X-ray binary system is another natural laboratory. another probe of the neutron star interior that we could never build on Earth. The neutron star sits at the center of the expanding debris cloud, spinning. This is critical. The original massive star was rotating. When the core collapsed from an Earth-sized ball to a sphere 20 kilometers across, it conserved its angular momentum. The same physical principle that makes a figure skater spin faster when they pull their arms in, just applied to something collapsing from Earth radius to city radius. The result is a neutron star rotating extraordinarily fast. Newly formed neutron stars may spin tens or hundreds of times per second. As they radiate energy through their intense magnetic fields, they slow down over time. But some never slow down much. Some neutron stars are in binary systems where material from a companion star falls onto them, carrying angular momentum, spinning them back up to extraordinary rotational speeds over millions of years. The fastest known pulsar, PSR J 1748-2446 AD, in a globular cluster called Terzan, 5 rotates 716 times per second. 716 complete rotations per second for an object 20 kilometers across. To put that in physical terms, the equatorial surface of that neutron star is moving at roughly 24% of the speed of light. Not close to the speed of light in the way a fast aircraft is close to a bicycle. Meaningfully, relativistically close to the speed of light. A quarter of c. At that speed, the surface is moving fast enough that relativistic effects are significant. The star is slightly oblate from the centrifugal forces. The general relativistic corrections to its moment of inertia are not negligible. These rapidly rotating neutron stars, when their beams of radio emission happen to sweep across Earth with each rotation, are called pulsars. And they are among the most precisely timed objects in the observable universe. Some pulsars keep time more accurately than the best atomic clocks on Earth. When the first pulsar was discovered in 1967 by Jocelyn Bell Burnell and her supervisor Anthony Hewish at Cambridge, the signal was so regular and so unexpected that the team briefly considered whether it might be an artificial signal from an extraterrestrial civilization. They nicknamed the source LGM-1, Little Green Men. The pulses were arriving with a period of 1.337 seconds, with a stability that seemed to imply artificial origin. Then, more pulsars were found, and the hypothesis collapsed. Nature had built a clock, not through engineering, through physics, through the combination of rapid rotation, conserved angular momentum, and a beam of radiation that sweeps across the cosmos with mechanical precision. What Bell Burnell had detected was the rotation of a neutron star, the lighthouse in the dark. The interior of a neutron star also hosts one of the most extreme thermal environments in the universe. For the first few minutes after a neutron star forms in a supernova, the interior is opaque, even to neutrinos. The density is so high and the temperatures so extreme that neutrinos can't escape freely. They're trapped. The star in this phase is called a proto-neutron star. It's hot, lepton-rich, and in a different thermodynamic state from the cold neutron stars we observe centuries and millennia later. The proto-neutron star radiates its enormous heat load primarily through neutrino diffusion, neutrinos slowly working their way outward through the dense matter, losing energy with each interaction until they reach the neutrinosphere, the surface from which neutrinos can escape freely. The neutrino luminosity of a proto-neutron star is staggering. For the first few seconds after formation, A single proto-neutron star is radiating more energy per second in neutrinos than the entire observable universe radiates in visible light. Not a galaxy. The entire observable universe. One object. For a few seconds. This is not hyperbole. The numbers come directly from the physics. The total energy released is around 3 × 10 to the power of 46 joules, mostly in the first 10 seconds. The neutrinos detected from supernova 1987 A captured the tail end of this phase. Those 24 particles from 160,000 light-years away were a tiny fraction of the torrent. The proto-neutron star cools over roughly 30 seconds. As the neutrino luminosity drops, the neutrinosphere recedes, and the interior becomes increasingly transparent. The transition from proto-neutron star to cold neutron star takes roughly a minute, and then the star enters the long cooling phase that lasts millions of years. During the proto-neutron star phase, the equation of state is different. The high temperatures and trapped neutrinos change which phases of matter are stable. Hyperons that might not appear in cold neutron stars could appear in the hot proto-neutron star. Quark matter transitions might happen at different densities. The physics of proto-neutron stars is therefore a separate but related question to the physics of cold neutron stars. Neutrino observations of future nearby supernovae, if we're fortunate enough to see one within a few kiloparsecs, will give us a direct probe of the proto-neutron star phase. Current neutrino detectors, vastly improved since the supernova 1987A era, would detect thousands of neutrinos from a Milky Way supernova. The time profile, the energy spectrum, the total fluence, all would carry information about the equation of state in the proto-neutron star phase. We're waiting for the next nearby supernova. It could happen tomorrow. It could be thousands of years away. But when it does, the neutrino detectors are ready. The story of how neutron stars were predicted before they were discovered is remarkable. In 1933, just 1 year after the neutron itself was discovered by James Chadwick, 2 physicists named Walter Baade and Fritz Zwicky proposed the existence of neutron stars. They were trying to explain supernovae. Zwicky had spent years systematically photographing galaxies and identifying new bright spots that appeared and faded supernovae. He and Baade recognized that these events released enormous amounts of energy. They proposed that the energy source was the collapse of an ordinary star into a star composed mainly of neutrons packed closely together. A neutron star. The proposal was made in a short paper presented at a meeting of the American Physical Society in December 1933. The entire relevant paragraph was only a few sentences long. It was, by any measure, one of the most prescient scientific predictions ever made. At the time, it was largely ignored. Neutron stars seemed too exotic. The physics of how a star could collapse to nuclear density wasn't understood. The idea sat largely dormant for decades. In the 1940s and 50s, theorists began working out the physics of stellar collapse in more detail. J. Robert Oppenheimer, who would later lead the Manhattan Project, and his collaborators worked out the general relativistic structure of neutron stars in 1939. The Oppenheimer-Volkoff equation describes how the pressure inside a neutron star must support the weight of the material above it against gravity, incorporating the full machinery of general relativity. It's one of the fundamental equations of neutron star physics. Oppenheimer's paper also made a disturbing prediction. Above a certain mass, the Oppenheimer-Volkoff limit, which he estimated at about 7/10 of a solar mass. Though more accurate calculations put it closer to 2 to 3 solar masses, a neutron star cannot hold itself up. It must collapse further. Into what? The paper left open. The answer, which we now call a black hole, was only worked out in the following decades. The field sat in relative dormancy until 1967, when Jocelyn Bell Burnell discovered the first pulsar. The recognition that pulsars were rotating neutron stars came almost immediately. Bardey and Zwicky's 34-year-old prediction was confirmed. The neutron star was real, and the era of neutron star astrophysics began. Now comes the part where ordinary language starts to fail. We need to go inside. And once we go inside, the physics starts doing things that have no everyday analogies. The surface of a neutron star isn't soft. It isn't liquid. It's a crust, a crystalline lattice of atomic nuclei, mostly iron and nickel, arranged in a rigid grid, compressed to densities thousands of times greater than anything on Earth. The crust is perhaps a kilometer thick. It is the outermost layer, and it's already more extreme than anything in our solar system. Think of the crust as the last outpost of something recognizably like matter. Down here, you still have atomic nuclei. They're distorted, they're compressed. The electrons between them are unbound and free, making the crust a conductor, but the nuclei themselves still exist as discrete, identifiable objects. Iron nuclei in a lattice. The outermost layer of the crust, just beneath the thin atmosphere of a neutron star, has a density of around 1,000,000 grams per cubic centimeter. That is 1,000,000 times the density of water. Lead has a density of about 11 grams per cubic centimeter. The outer crust of a neutron star is nearly 100,000 times denser than lead, and that's the lightest part. As you descend through the crust, the density increases steadily. At some depth into the crust, roughly a few hundred meters below the surface, the density becomes high enough that free neutrons appear. Not neutrons bound inside nuclei. Free neutrons dripped out of the nuclear lattice by the pressure, forming a sea between the nuclei. This is called the neutron drip point. Below the neutron drip point, the interior is a mixture of nuclei embedded in a fluid of free neutrons, plus free electrons, maintaining overall charge neutrality. The nuclei in this region start to deform. In ordinary matter, atomic nuclei are roughly spherical. A proton is spherical, a neutron is spherical, and small nuclei are also roughly spherical. Under the pressures inside a neutron star crust, they start losing that shape. They flatten into disks. Then they elongate into rods. Then the rods merge into sheets. Physicists who study neutron stars have given names to these exotic nuclear structures. Nuclear pasta. Not as a joke, this is the actual terminology used in the peer-reviewed literature. Gnocchi, spaghetti, lasagne. The shapes are named after pasta because the shapes actually resemble pasta. Gnocchi, round blobs of nuclear matter embedded in a sea of free neutrons. Spaghetti, long thin cylinders of nuclear matter stretching through the layer. Lasagne, flat sheets of nuclear matter alternating with layers of neutron fluid. Anti-gnocchi, holes of neutron fluid in a background of nuclear matter. Anti-spaghetti, cylindrical tunnels of neutron fluid threading through the nuclear background. In each case, the actual material is atomic nuclei, so compressed and distorted that they've lost all resemblance to the discrete, separate objects we call atoms. nuclear pasta is predicted to be the strongest material in the universe. Calculations suggest it would require more energy per unit area to break a piece of neutron star pasta than to blow up a mountain. The breaking stress of nuclear pasta, according to theoretical modeling published in peer-reviewed journals, is around 10 billion pascals. By comparison, the strongest steel on Earth has a breaking stress of around 2 billion pascals. Neutron star crust is 10 billion times stronger than the strongest steel we can make. And that's just the outermost layer. Below it, things get stranger. As you descend through the crust and into the outer core, the last remnants of atomic structure disappear. Individual nuclei dissolve. The density here exceeds nuclear saturation density, roughly 2.3 times 10 to the power of 17 kilograms per cubic meter. The density at which individual neutrons and protons are packed together so closely they're essentially in contact. At this point, the protons and neutrons have lost their individual memberships in specific nuclei. There are no more nuclei. There is just a dense fluid of neutrons, with a smaller admixture of protons and electrons, all coexisting in an uneasy quantum equilibrium. This outer core fluid has properties unlike anything in ordinary matter. The first and most striking of those properties is superfluidity. Superfluidity is a quantum mechanical state of matter in which a fluid flows with literally zero viscosity, zero resistance to flow. If you stir a superfluid in a closed container, it never stops flowing. Not because friction is very small, because there is none. The fluid will circulate forever because there is no mechanism by which it can lose its kinetic energy. On Earth, superfluidity has been demonstrated with helium cooled to within a few thousandths of a degree above absolute zero. When liquid helium is cooled below 2.17 Kelvin, a temperature called the lambda point, it transitions into a superfluid phase. The superfluid helium flows up and over the walls of its container, seeps through glass, creates a persistent current that doesn't decay. Scientists have sealed superfluid helium in a torus and measured its circulation years later. It was still going, unchanged. And a current that had been set in motion years before, still circulating, because superfluidity allows no friction to slow it. Inside a neutron star, the neutrons in the outer core are predicted to be in a superfluid state throughout essentially the entire volume. But here is what makes this remarkable. Neutron star superfluidity is not the result of extreme cold. The interior of a newborn neutron star is around 100 billion degrees. After hundreds of thousands of years of cooling, it's still hundreds of millions of degrees. Superfluidity at those temperatures sounds like an impossibility. In ordinary materials, superfluidity is a low-temperature phenomenon. Helium becomes a superfluid at 2 degrees above absolute zero. Ordinary superconductors work at tens of degrees above absolute zero. The idea of a superfluid at hundreds of millions of degrees seems paradoxical, but it isn't. The neutrons in the outer core form Cooper pairs bound together by the residual strong nuclear force in a way that lowers their total energy. The Cooper pair is a concept from condensed matter physics. In ordinary superconductors, electrons pair up through a mechanism mediated by vibrations in the crystal lattice. Once paired, they can condense into a quantum ground state where they move collectively without any individual scattering. The same mathematics applies to neutrons in a neutron star, but with a crucial difference. The binding is mediated by the strong nuclear force, not by crystal lattice vibrations. The strong force is far more powerful than the electromagnetic interactions that mediate ordinary Cooper pairs. So the energy gap for pair breaking, the energy you'd have to supply to break a neutron Cooper pair, is far larger than in any ordinary superconductor, large enough to survive at temperatures of hundreds of millions of degrees. The neutron pairs are bound so tightly that thermal fluctuations at those temperatures can't break them. The result is a superfluid that exists not despite the temperature, but independently of it, because the pairing energy scale is simply far above the thermal energy scale. The superfluid interior of a neutron star has measurable, observable consequences. When a neutron star's rotation slows slightly as pulsars do, gradually, as they radiate energy through their magnetic fields, they occasionally do something unexpected. They speed up. Suddenly, briefly. These sudden increases in rotation rate are called glitches. The first pulsar glitch was observed in Vela, a pulsar roughly 1,000 light-years away, in 1969, just 2 years after pulsars were discovered. The Vela pulsar suddenly sped up by about 0.02% in its rotation rate. That sounds tiny. But a neutron star is not supposed to speed up. It's supposed to slow down. Always. The fact that it can spontaneously spin faster means something unexpected is happening inside. The current best explanation involves the superfluid neutrons in the interior. The superfluid neutrons rotate not as a bulk fluid, but through a lattice of quantized vortices, thin threads of rotating superfluid threading through the star from top to bottom. In a rotating superfluid, the rotation is carried entirely by these vortex lines, each one carrying a fixed, quantized amount of angular momentum. When the superfluid spins faster, the vortex lines move apart. When it slows down, they move closer together. There may be 10 to the power of 17 such vortex lines threading through the interior of a typical neutron star. These vortex lines can pin to imperfections in the crust, crystal defects, nuclear puster structures, interfaces between different phases. When the crust slows down due to magnetic braking, the pinned vortex lines stay put. The superfluid beneath continues rotating at its old speed. A differential builds up between the superfluid and the crust. The superfluid is spinning faster than the visible star. This mismatch stores angular momentum. Eventually, the stored stress exceeds what the pinning can hold. The vortex lines unpin and move outward all at once. When vortices move outward in a rotating superfluid, angular momentum is transferred from the superfluid to the crust, spinning the crust up. The observable pulsar, which is the crust, suddenly rotates faster. A glitch. The spin-up happens in less than a minute for most pulsars. The subsequent slow recovery, as the crust and interior re-equilibrate, can last weeks or months. The details of glitches, their frequency, their size, the recovery timescale, are one of the few direct observational probes we have into the interior of a neutron star. Different models of the interior predict different glitch statistics. By cataloging glitches across many pulsars over many years, astronomers are building a database that constrains what's happening several kilometers below any surface we can observe. More than 500 glitches have now been recorded across roughly 180 pulsars. Each one, a seismometer reading from the interior of an object we can never visit, never sample, never directly inspect. Each one, a message from the superfluid inside. Protons in the outer core are predicted to be in a superconducting state. Superconductivity is the electromagnetic analog of superfluidity. In a superconductor, electrical current flows with zero resistance. Not very low resistance. Zero. In ordinary conductors, electrons scatter off atomic vibrations and impurities as they move, losing energy as heat. That's why wires get warm when current flows through them. In a superconductor, electrons pair up and condense into a quantum ground state where scattering is forbidden. Currents flow forever without losing energy. The physics of the pairing is the same as for the superfluid neutrons' Cooper pairs, but this time it's protons pairing up, and the result is superconductivity rather than superfluidity, because protons carry charge and the condensed state has electromagnetic properties that a neutral superfluid doesn't. The superconducting protons in the outer core have profound consequences for the magnetic field of the neutron star. In an ordinary conductor, a magnetic field can penetrate the material freely. In a superconductor, something remarkable happens. The superconducting state expels magnetic flux from its interior, the Meissner effect. But in a Type II superconductor, the flux is not expelled completely. Instead, it's confined into discrete, quantized tubes, called flux tubes, that thread through the material. Each flux tube carries a fixed quantum of magnetic flux. The total magnetic flux in the star is divided among billions of these tubes. The neutron star core is a Type II superconductor, and the proton flux tubes thread through the superfluid neutron vortices. The two systems, the superfluid and the superconductor, are interlocked. The vortex lines and flux tubes interact. They exert forces on each other. They move together or drag each other along when the rotation rate or magnetic field changes. This coupling between the superfluid neutrons and the superconducting protons is one of the reasons the physics of a neutron star interior requires simultaneously applying nuclear physics, condensed matter physics, and general relativity. No other object requires all three simultaneously to even begin to describe. Neutron stars have the strongest magnetic fields of any known objects in the universe. Ordinary pulsars have surface magnetic field strengths around 10 to the power of 8 Tesla. For reference, the strongest continuous magnetic field produced in a human laboratory is about 45 Tesla. A pulsar's surface field is roughly 2 million times stronger. Some neutron stars, a special class called magnetars, have surface fields around 10 to the power of 11 Tesla. 100 billion Tesla. To try to convey what that means, Earth's magnetic field is about 50 microtesla. A strong clinical MRI machine runs at around 3 Tesla. The record for a sustained laboratory magnetic field is about 45 Tesla. A magnetar's surface field is roughly 2 billion times the laboratory record. At those field strengths, the vacuum itself behaves differently. Quantum electrodynamics predicts that a sufficiently strong magnetic field can spontaneously pull apart the quantum vacuum into pairs of electrons and their antimatter counterparts, positrons. Virtual pairs of particles and antiparticles exist fleetingly in the vacuum at all times, appearing and annihilating in fractions of a second. At ordinary field strengths, they don't become real. At the quantum critical field around 4.4 times 10 to the power of 9 Tesla, the field is strong enough to drag a virtual pair apart before they can annihilate, converting them into real particles. The energy of the magnetic field converts directly into matter. Magnetars exceed this threshold. Their fields are strong enough to trigger spontaneous pair production in the space around them. The structure of atoms near a magnetar's surface is also altered beyond recognition. The magnetic force on electrons, orbiting atoms near the surface, is stronger than the electrostatic force binding those electrons to their nuclei. Electrons are dragged into orbits, aligned with the magnetic field lines. Atoms are stretched into thin needles, aligned with the field. The periodic table, as you know it, does not apply near a magnetar. Hydrogen near the surface is a metallic conductor. Carbon forms unusual bonding arrangements that have no analogue in ordinary chemistry. The chemical properties that define elements and make ordinary chemistry possible are only valid in a particular regime of magnetic field strength. Change the field enough, and you change what atoms are. You change how matter is structured at the most basic level of chemistry. Magnetars announce themselves through sudden releases of energy called starquakes and flares. When the crust of a magnetar fractures under the electromagnetic stress cracked by the enormous forces exerted by the field on the conducting crust, the way rock fractures in an earthquake, the magnetic field lines attached to the crust shift suddenly. The enormous energy stored in the field, which in a magnetar is one of the largest reservoirs of magnetic energy in the universe, is partially released in milliseconds. There's a subset of neutron stars that sit in a category all their own. Isolated neutron stars with no companions, not pulsing in radio, not accreting anything, that are detected purely by their fading X-ray glow. Some of them are known as the Magnificent Seven, not a movie title. A nickname used by neutron star astronomers for seven nearby, thermally emitting, isolated neutron stars found by the Rosat X-ray satellite in the 1990s. These objects are remarkable because they allow direct measurement of the surface emission without the complications of an accretion disk or a companion. Their spectra show the thermal emission of the neutron star surface itself. Some of them show spectral features, absorption lines at specific X-ray energies that carry information about the surface magnetic field and the gravitational redshift. But the identification of these spectral lines has been frustratingly difficult. The lines don't correspond to any known atomic transition at the rest frame energies of common elements. Either they're highly shifted by gravity and magnetism in ways that are hard to model, or they correspond to transitions in exotic, magnetically compressed atoms that haven't been fully calculated. The Magnificent Seven are some of the closest neutron stars to Earth. The nearest, RxJ 1856.5-3754, is roughly 400 light-years away. The fact that we can observe neutron star surface emission directly, without the complicating factor of accretion, makes them valuable. But extracting the equation of state information from thermal spectra requires accurate atmosphere models of what the thin layer of atoms above the pure neutron star surface looks like, how it absorbs and emits radiation. Those models are complex and uncertain. The combination of magnetic field effects, gravitational effects, and thermal emission from a pure nuclear surface is a calculation at the edge of what current theory can reliably produce. Even the nearest neutron stars are holding their secrets carefully. On December 27, 2004, a magnetar called SGR 1806-20, roughly 50,000 light-years from Earth, released more energy in a fraction of a second than the Sun radiates in approximately 250,000 years. In about 0.2 of a second, the burst of gamma rays swept through the outer solar system and reached Earth. It ionized the upper atmosphere. It disrupted radio communications. It was detected by satellites and ground-based telescopes all over the planet. from 50,000 light-years away. The 2004 event was the brightest transient event ever recorded from outside our solar system, and it lasted less than a second. If SGR 1806-20 were as close to us as the nearest star 4 light-years, that single burst would have been sufficient to strip away the Earth's ozone layer entirely, and the consequences for surface life would have been severe. That's the output of an event that lasted less than a second, from an object we never could have seen with the naked eye at its actual distance. Magnetars are relatively rare. There are about 30 known, out of the roughly 2,000 identified pulsars, but they're extraordinarily important to understanding the diversity of neutron star behavior. Magnetars are thought to form when the original stellar collapse creates a proto-neutron star with particularly rapid rotation, fast enough that convective instabilities inside the hot, newly formed star can amplify the seed magnetic field to extraordinary strengths through a dynamo mechanism. A rapidly rotating, convecting, conducting fluid generates magnetic field by the same basic process that generates Earth's magnetic field and the Sun's magnetic field. But in a proto-neutron star, the rotation is far faster, the convection is far more vigorous, and the timescales are far shorter. The result can be a field 10,000 times stronger than an ordinary pulsar's. Once that field is in place, it dominates the neutron star's behavior. The magnetic braking is so intense that magnetars slow down rapidly. Most magnetars are young tens of thousands of years old. Older ones have slowed so much their magnetic energy has been substantially depleted. The magnetar phase of a neutron star's life is intense and brief. But while it lasts, it produces the most energetic events per unit time of any object in the universe. The role of hyperons, strange particles, heavier than neutrons, and protons in neutron star cores is one of the most actively debated questions in the field. Hyperons are baryons that contain at least one strange quark. The lightest are the lambda hyperon and the sigma hyperons. They're unstable. In ordinary matter, a lambda, for instance, has a half-life of about 0.2 of a nanosecond before decaying back to a proton and a pion. But in the dense interior of a neutron star, something changes. At sufficiently high densities, it can become energetically favorable for neutrons to convert into hyperons through weak interactions. The conversion reduces the Fermi pressure, the quantum mechanical pressure arising from the exclusion principle, because hyperons are heavier than neutrons and therefore fill their energy levels differently. New types of particles appear, spreading the population across more species, reducing the pressure contribution of each species. This softening of the equation of state, if hyperons appear, is called the hyperon puzzle. It's a puzzle because the softer equation of state predicts lower maximum neutron star masses. And observations of 2 solar mass neutron stars constrain the maximum mass to be at least 2 solar masses. If hyperons appear at the densities typical of neutron star interiors, the maximum mass predicted by most models drops below 2 solar masses, which is inconsistent with what we observe. There are several proposed resolutions. One is that hyperons simply don't appear because the repulsive interactions between hyperons and nucleons at high density are stronger than models predict, keeping the equation of state stiff enough. The hyperon-nucleon and hyperon-hyperon interactions are poorly measured. We have very limited laboratory data on these interactions at the relevant energies. Another resolution is that hyperons do appear, but the equation of state is stiffened by 3 body forces, or by a transition to quark matter at slightly higher density that compensates for the softening from hyperons. A third resolution is that the nuclear physics models are simply wrong in this regime, missing some repulsive effect that would prevent hyperon formation. Experimental programs at facilities like J-Park in Japan and FAIR in Germany are trying to measure hyperon-nucleon interactions more precisely to constrain which scenario is correct. Meanwhile, each new neutron star mass measurement above 2 solar masses tightens the constraint on hyperon models. If a neutron star with a mass of 2.5 solar masses is confirmed, the hyperon puzzle becomes more acute. If the maximum mass turns out to be genuinely close to 2 solar masses, hyperons are more plausible. The resolution is in the data. We just need more of it, more precise, from more objects. Neutron stars in globular clusters have a unique history. Globular clusters are dense balls of stars, each containing anywhere from 100,000 to several million stars, packed into a sphere perhaps 100 light-years across. The stellar density at the center of a globular cluster can be millions of times the stellar density near our Sun. In such dense environments, stars interact with each other gravitationally far more frequently than in the open field of the galaxy. Encounters between stars, close passages, captures, exchanges are common on astronomical timescales. This changes the evolution of neutron stars dramatically. A neutron star, formed in a globular cluster, might, over hundreds of millions of years, capture a companion through a close gravitational encounter. Or it might exchange into an existing binary, displacing one of the original stars. These interactions can put neutron stars into tight orbits with companions, low-mass stars, white dwarfs, or even other neutron stars that wouldn't exist if the stars had formed in isolation. The result is a disproportionately large number of millisecond pulsars in globular clusters. Although globular clusters contain a tiny fraction of the galaxy's stars, they contain a hugely disproportionate fraction of the galaxy's millisecond pulsars. The densest globular clusters, Terzan 5 and 47 Tucanae, in particular, are extraordinarily rich in millisecond pulsars. Terzan 5 alone contains over 30 known millisecond pulsars, including PSRJ 1748-2446 AD, the fastest spinning pulsar known. These globular cluster pulsars are valuable because their high density of neutron stars makes mergers more frequent than in the field. Neutron star mergers in globular clusters contribute to the observed gravitational wave background. And studying the millisecond pulsar population in globular clusters gives insight into the recycling mechanism, the process by which old, slow neutron stars are spun up to high rotation rates by accreting material from a companion. The recycled pulsar is one of nature's most elegant demonstrations of angular momentum conservation. A neutron star that formed millions or billions of years ago, slowed by magnetic braking to a near stop, then rejuvenated by centuries of accreted material carrying angular momentum, now spinning hundreds of times per second as a precisely timed clock. Recycled from the inside out by physics. Now we reach the region where physics becomes genuinely uncertain. The inner core, the very center of a neutron star. The central density of a neutron star is predicted to reach somewhere between 5 and 10 times nuclear saturation density. Nuclear saturation density is the density at which neutrons and protons are packed together as closely as they naturally go in a normal atomic nucleus. It's the density at which nuclear matter is in equilibrium with the attractive and repulsive components of the nuclear force balanced. 5 to 10 times that density is territory, where individual neutrons and protons may not be able to maintain their individual identities. Because neutrons and protons are not fundamental particles. Each one is made of 3 quarks bound together by gluons through the strong nuclear force. The theory that describes this is called quantum chromodynamics, or QCD. It is one of the most mathematically powerful theories in all of science, and one of the most computationally intractable. In ordinary matter, quarks are always confined inside protons or neutrons. You can never observe a free quark. If you try to pull 2 quarks apart, the force between them grows stronger the further you pull, until at some point it becomes energetically cheaper for the field to produce a new quark-antiquark pair from the energy you're putting in than to continue separating the originals. You end up with 2 mesons rather than 2 separated quarks. This is why free quarks don't exist in our world. They're always confined. But at the densities present at the centers of neutron stars, something changes. When matter is packed so tightly that the quarks from neighboring neutrons and protons start to overlap, when the average distance between quarks from different baryons approaches the size of the placed baryons themselves, the concept of confinement starts to lose meaning. The quarks can't be confined to 1 neutron or 1 proton, when the neutrons and protons themselves no longer have well-defined boundaries. They become shared across the entire volume. A sea of quarks, liberated from their confinement, flowing as a new kind of fluid. This state of matter is called quark matter, and it may exist right now, at the center of every neutron star in the galaxy. Quark matter is not a single, well-defined state. Depending on the density, the temperature, and the ratio of different quark flavors present, it can exist in a variety of phases, several of which have no analogues whatsoever in ordinary matter. The most discussed is color superconductivity. In ordinary superconductors, electrons pair up through a mechanism mediated by vibrations in the crystal lattice, the phonon-mediated BCS mechanism, developed in 1957 by Bardeen, Cooper, and Schrieffer. The same mathematical framework applies to quarks at high density. Quarks, near their Fermi surface, can pair up with the pairing mediated by gluon exchange rather than phonon exchange. When they condense into a coherent quantum ground state, you get color superconductivity. But quarks come in different varieties. There are 6 types of quark called flavors, named up, down, strange, charm, bottom, and top. In ordinary matter, at low temperatures, only up and down quarks are relevant. Strange quarks are slightly heavier and don't appear in ordinary protons or neutrons. But at the densities inside neutron stars, the energy involved is high enough that strange quarks can be produced through weak interactions. Their presence changes the pairing possibilities dramatically. When up, down, and strange quarks are all present, they can pair with each other in different combinations. The different pairing patterns correspond to different phases of color superconducting matter. The most symmetric is the color flavor locked phase. In this phase, up quarks, down quarks, and strange quarks pair with each other in a pattern that locks color degrees of freedom to flavor degrees of freedom. Every symmetry of the system, color symmetry, flavor symmetry, electromagnetic symmetry, baryon number symmetry, breaks simultaneously. The mathematics of this symmetry breaking is beautiful and complex, involving group theory from abstract algebra, topological defects, called color magnetic vortices, and analogies to the Higgs mechanism that gives elementary particles their mass. At intermediate densities, where strange quarks are just beginning to appear, a simpler two-flavor color superconductor is predicted. At even higher densities, if quarks form pairs with non-zero momentum, the result is a crystalline color superconductor, a quark crystal, a lattice structure formed from quantum field theory rather than from atoms. None of this has been directly observed inside a neutron star, but neither is it speculation without foundation. It is the predicted consequence of QCD, a theory that has been tested to extraordinary precision in particle accelerators applied to a new regime of density. The problem is that the regime of cold dense matter at neutron star densities is one where QCD cannot be solved exactly. The mathematical techniques that work beautifully for QCD at high energies, perturbative expansions, break down at neutron star densities. Lattice QCD. The computational technique for solving QCD numerically on a discretized spacetime grid suffers from a technical obstruction called the sign problem at high baryon density, making it exponentially expensive to compute. The regime that matters most is the one that is hardest to calculate. This is not unusual in physics. The problems that resist solution are the ones that reveal the limits of our tools. And the tools are slowly improving. Alongside quark matter, there's a more radical possibility called the strange quark matter hypothesis. In the 1980s, physicists Edward Witten and Arnold Bodmer independently proposed that strange quark matter, a mixture of up quarks, down quarks, and strange quarks in roughly equal proportions, might actually be the most stable form of matter in the universe. More stable than iron. More stable than anything in the periodic table. If this hypothesis is correct, then the true ground state of matter, the configuration it would adopt given enough time and the right conditions, is not iron. It is strange quark matter. The reason ordinary matter hasn't converted to this state is that the conversion requires crossing an enormous energy barrier. To convert a chunk of ordinary matter to strange quark matter would require converting an enormous number of quarks simultaneously. Because any intermediate state with only a few strange quarks would be less stable than both the starting material and the end product. This barrier is essentially impenetrable at ordinary pressures and temperatures. But inside a neutron star, where the pressures are sufficient to produce strange quarks in large numbers, the conditions might allow the conversion to begin. If it does begin, and if strange quark matter is truly the ground state, the conversion would propagate through the entire interior. Objects called strange stars might exist. Strange stars would look superficially like neutron stars. From the outside, similar masses, similar radii, similar rotation rates. But their interior would be entirely strange quark matter. The surface of a strange star would differ from a neutron star surface in subtle but potentially observable ways. The density at the very surface would drop discontinuously from nearly zero to a high value over a distance of a few femtometers, rather than building up gradually through a crust. The oscillation modes of a strange star would differ from those of a neutron star. The cooling rate would differ. Every neutron star observation we make is also a test of the strange star hypothesis. After decades of observations, no observation has conclusively ruled it in or out. The question remains genuinely open. Beyond strange quark matter, theorists have proposed a state called a quark-gluon plasma. in which not only the quarks, but the gluons, mediating the strong force, become deconfined, and the entire system is a thermal plasma of fundamental particles rather than composite ones. Quark-gluon plasma has been created in particle accelerators at the Large Hadron Collider at CERN and the relativistic Heavy Ion Collider at Brookhaven by colliding heavy nuclei at nearly the speed of light. The collisions create a tiny, extraordinarily hot fireball that exists for about 10 to the power of negative 23 seconds before cooling and condensing into ordinary particles. It is the hottest matter ever produced by human beings. Temperatures around 10 trillion degrees. And it behaves not as a gas, as theorists initially expected, but as a nearly perfect fluid. The sheer viscosity of the quark-gluon plasma is so low, close to the theoretical minimum allowed by quantum mechanics, that it flows more smoothly than any known liquid. Water, oil, even liquid helium. At low temperatures, none of them flows as smoothly as the quark-gluon plasma produced in collider experiments. The conditions inside a neutron star core are cold compared to the collider. Plasma hundreds of millions of degrees rather than trillions. But the density is orders of magnitude higher. Whether cold, dense quark matter and hot dilute quark-gluon plasma are the same phase of matter or different phases connected by a phase boundary is an active research question. The phase diagram of QCD, the map of what states quark matter occupies at every combination of temperature and density, has been partially charted at high temperatures by collider. Experiments. The high density, lower temperature region, relevant to neutron star interiors, remains largely uncharted. Mapping it is one of the central goals of nuclear astrophysics and high-energy physics for the coming decades. The moment of a neutron-star merger is one of the most computationally demanding physical processes to simulate. Understanding what happens in the milliseconds around the merger of two neutron stars requires numerical relativity, solving Einstein's equations on a supercomputer grid, combined with neutrino transport, magnetic field evolution, and general relativistic hydrodynamics simultaneously. These simulations are among the most complex scientific calculations performed by any research group in any field. The challenge is that general relativity is 10-coupled, non-linear, partial differential equations. Each one depends on all the others. There's no simple, sequential way to solve them. You have to evolve all 10 simultaneously on a three-dimensional spatial grid, stepping forward in time in small increments, checking that the solution remains stable and consistent at each step. For a neutron-star merger, the grid has to be fine enough to resolve the neutron stars themselves, tens of kilometers across, while also being large enough to track the gravitational waves as they propagate outward. Hundreds of kilometers. The resolution required to accurately model the tidal disruption of the neutron stars as they approach merger is finer still. And inside the merger remnant, the densities are high enough that the equation of state is being probed at its limits. The simulations have to incorporate a realistic equation of state. But since the equation of state is what we're trying to figure out, the simulations are run for many different assumed equations of state, and the predicted gravitational wave signals are compared to observations to see which equation of state is most consistent. It's circular in a productive way. The observations constrain the simulations. The simulations help interpret the observations. Together, they narrow the allowed parameter space. Current simulations can run on clusters of thousands of processors for weeks to model a single merger event. They've taught us that the remnant of two merging neutron stars, if it survives for more than a few milliseconds, oscillates at characteristic frequencies that depend on the total mass and the equation of state. These oscillation frequencies are in the range of 2 to 4 kilohertz. Gravitational wave detectors, sensitive enough to detect these frequencies from nearby mergers, would essentially be performing spectroscopy on the post-merger remnant, reading off its internal resonances the way a spectroscopist reads off the frequencies of atomic transitions. The next generation of detectors is being designed partly to achieve exactly this. General relativity is not an approximation near neutron stars. It is a necessity. Near a neutron star, space-time is significantly curved. The surface gravity of a neutron star is roughly 200 billion times the surface gravity of Earth. The photons that leave the surface of a neutron star are gravitationally redshifted. As they climb out of the deep gravitational well, they lose energy. Light, that was X-rays at the surface, arrives at our telescopes as softer X-rays, or even ultraviolet. The amount of this redshift depends on the compactness of the star, the ratio of its mass to its radius. Measuring the redshift of known atomic spectral lines in the X-ray emission from neutron star surfaces is another way to determine this ratio. If you can identify a spectral line and measure how much it's been shifted toward lower energies, you can calculate how deep the gravitational well it climbed out of is. Every such measurement is another constraint on the equation of state. There's also a general relativistic effect called frame dragging. A rotating massive object doesn't just curve spacetime. It drags spacetime around with it, the way a spinning ball drags the fluid surrounding it. Near a rapidly rotating neutron star, spacetime itself is being carried around by the rotation of the star. The effect is tiny at the distances where we observe neutron stars, but it's measurable through precise pulsar timing in binary systems. And time itself runs differently near a neutron star. Clocks on the surface of a neutron star tick at roughly 60 to 70% the rate of clocks far from it. This is not a metaphor. It is a direct prediction of general relativity, confirmed to extraordinary precision in dozens of independent experiments. If you could somehow spend 1 year on the surface of a neutron star, by your own reckoning, an observer watching you from far away would see roughly a year and a half pass from their perspective. Your year is shorter than theirs. Not because time feels different, because time genuinely passes at a different rate in a deep gravitational well. The most precisely confirmed predictions of general relativity have come from binary pulsar systems. When two massive objects orbit each other in a binary, they lose energy by radiating gravitational waves. The orbit shrinks. The orbital period decreases by a measurable, predictable amount. In 1974, Russell Hulse and Joseph Taylor discovered the first binary pulsar, PSRB, 1913-16, a pulsar and its companion neutron star orbiting each other every 7.75 hours. They measured the decrease in the orbital period over years of observation. It matched the general relativistic prediction for energy loss through gravitational wave emission to within less than 0.1%. The Nobel Prize in Physics in 1993 was awarded to Hulse and Taylor for this discovery. It was the first indirect evidence for gravitational waves, confirmed by watching two neutron stars slowly spiraling toward each other. Binary neutron star systems are extraordinary objects that have taught us more about gravity than almost any other astronomical phenomenon. When two neutron stars orbit each other, the system is a laboratory for general relativity under extreme conditions. The orbital periods can be as short as a few hours. The orbital velocities can be a significant fraction of the speed of light. The gravitational fields are strong enough that Newtonian gravity is inadequate to describe the orbits. Every effect predicted by general relativity, gravitational time dilation, frame dragging, the precession of the orbital ellipse, the shrinkage of the orbit due to gravitational wave emission, is measurable and measurably large in binary neutron star systems. The double pulsar system, discovered in 2003, is the only known system where both neutron stars are pulsars. Named PSR J0737-3039, it consists of two pulsars, one spinning about 44 times per second, the other about once every 2.8 seconds, orbiting each other every 2.4 hours. Because both stars are pulsars, the timing of pulses from each can be used to precisely measure the orbit. The result is an extraordinarily precise test of general relativity. 7 independent predictions of general relativity have been tested in this system. All 7 match. The precision of agreement is at the level of a few parts in 10,000. This is the most precisely tested laboratory for general relativistic effects in strong gravitational fields outside the immediate vicinity of a black hole. The double pulsar is also spiraling together due to gravitational wave emission. The orbital period is decreasing at a rate that matches the general relativistic prediction for energy loss through gravitational waves. At the current rate, the two pulsars will merge in approximately 85 million years. When they do, they will produce an event similar to GW 170817, a burst of gravitational waves, a kilonova, a spray of heavy elements scattered into the interstellar medium. The double pulsar is also notable for a direct observation of relativistic spin-orbit coupling. The faster pulsar's spin axis is precessing rotating in space due to the gravitational interaction with its companion. The precession rate matches the general relativistic prediction for the geodetic precession of a spinning object in a curved spacetime. Because the spin precession changes the orientation of the beam relative to Earth, the profile of the faster pulsar's radio pulses has been slowly changing since discovery. Eventually, the beam will precess out of the line of sight and the faster pulsar will temporarily disappear. Calculations suggest this will happen within the next decade. The observation of this disappearance will itself be a test of general relativity. The direct evidence came in September 2015. Two black holes, each around 30 solar masses, merged roughly 1 billion light-years away. The gravitational wave signal, a chirp lasting less than a second, was detected simultaneously by the two LIGO detectors. The scientists who led LIGO, Rainer Weiss, Kip Thorne, and Barry Barish, were awarded the Nobel Prize in Physics in 2017. But the event that changed everything for neutron star physics came 2 years later. In August 2017, two neutron stars in a binary system, approximately 130 million light-years away, completed a merger that had been building for hundreds of millions of years. As the two neutron stars spiraled toward each other in the final seconds, losing energy to gravitational wave emission at a ferocious rate, the orbital frequency climbed from tens of hertz to hundreds of hertz. The gravitational wave signal swept upward in frequency, a chirp, just like the black hole mergers, but longer and with a distinctive character in its final moments. The event, designated GW170817, was detected by LIGO and Virgo, the European gravitational wave detector that had come online just weeks earlier. The timing between the three detectors allowed the direction to be localized to a region of sky about 28 square degrees. 1.7 seconds after the gravitational wave signal ended, a short gamma-ray burst was detected by the Fermi satellite and the Integral satellite. 90 seconds after that, the galaxy NGC 4993 in the constellation Hydra was identified as the host. And then telescopes around the world, radio, optical, infrared, ultraviolet, X-ray, converged on the source. Over the following days, they watched a kilonova unfold. An explosion powered not by thermonuclear reactions, but by the radioactive decay of heavy elements freshly synthesized in the collision. The optical colors, evolving from blue to red over days, matched models that included large quantities of lanthanide elements, heavy metals synthesized by the rapid neutron capture process in the dense, neutron-rich material ejected in the merger. Strontium was directly identified in the spectrum. Gold, platinum, and europium were consistent with the light curve models. The mass of gold synthesized in the GW170817 merger was estimated at roughly 10 times the mass of Earth. 10 Earth masses of gold, created in a few seconds of catastrophic violence between two neutron stars, ejected into space, eventually to be incorporated into new planetary systems. This was the first multi-messenger astronomical event in history, an event observed simultaneously in gravitational waves, gamma rays, X-rays, ultraviolet, optical, infrared, and radio. Every branch of observational astronomy contributing simultaneously to a single picture. And within the gravitational wave data was something else. Something that told us about the interior of the neutron stars themselves. When two neutron stars are close and spiraling fast, the intense gravitational field of each one raises a tidal bulge on the other. The shape of each star distorts slightly. This tidal deformation affects the orbital dynamics, which affects the gravitational wave signal in a way that depends on how easily the star can be deformed. A stiffer equation of state, a neutron star that resists compression more strongly, produces a less deformable star, which leaves a different imprint on the waveform. By analyzing the GW170817 signal in detail, physicists extracted a measurement of the tidal deformability. The analysis constrained the radius of a typical 1.4 solar mass neutron star to somewhere between 11 and 14 kilometers. For a field where "we don't know the radius" had been the standard position for decades, this was a transformation. It ruled out the most extreme equations of state, both the softest, which would make stars too compact and deformable, and the stiffest, which would make them too large and rigid. The allowed region narrowed. The picture sharpened. A single event, 130 million light-years away, told us something definitive about the interiors of neutron stars, that 50 years of observation had only been able to bracket loosely. The measurement of neutron star masses from pulsar timing had already transformed the field before GW170817. The technique called Shapiro delay gives mass measurements of extraordinary precision. When the radio pulses from a pulsar pass through the gravitational field of a companion star on their way to Earth, they travel a slightly longer path through curved spacetime than they would through flat space. They arrive slightly late. The amount of delay depends on the masses of both stars. By measuring the Shapiro delay, as the pulsar's orbit carries it behind its companion, from our perspective, the masses can be determined to high precision. In 2010, the pulsar PSR-J 1614-2230 was measured using this technique. The result: 1.97 solar masses. This was the most massive neutron star precisely measured at that time. It immediately ruled out a significant class of proposed equations of state, specifically those soft enough to predict a maximum neutron star mass below 2 solar masses. Any model in which the presence of exotic matter, hyperons, quark matter, softened the equation of state enough that it couldn't support 2 solar masses became inconsistent with observation. This became known as the hyperon puzzle. Some equations of state that included hyperons, strange baryons containing strange quarks, heavier cousins of the proton and neutron, predicted maximum masses well below 2 solar masses. Those models were ruled out. The constraint has been sharpened further. PSR J 0740-6620, measured in 2020 using a combination of NICER, X-ray data, and radio timing, came in at 2.08 solar masses. Whatever is inside a neutron star, whatever exotic matter might be present at the center, the equation of state must be stiff enough to support over 2 solar masses of material against gravity. That is a hard observational fact. The theory has to accommodate it. The NICER instrument, the Neutron Star Interior Composition Explorer, mounted on the International Space Station in 2017, brought a new technique to bear. NICER observes X-ray pulsars and extracts information about their size using pulse profile modeling. When there's a hot spot on the surface of a rotating neutron star, the X-ray brightness varies as the spot rotates in and out of view. In ordinary Newtonian physics, this modulation would be simple. But in general relativity, the calculation is more complex. The curvature of space-time bends the X-rays as they leave the surface. A hot spot on the far side of the star can still be seen because the light curves around the star. The apparent surface area is larger than the geometric surface area because space-time curvature acts like a lens. The shape of the resulting light curve, the specific way brightness rises and falls, encodes information about the compactness of the star, the ratio of its mass to its radius. By fitting detailed general relativistic models to NICER's X-ray light curves, researchers can simultaneously constrain the mass and radius of individual neutron stars. This is called pulse profile modeling, and it's extraordinarily difficult. The models involve many parameters: the size and temperature of the hotspot, the geometry of the magnetic field, the inclination of the spin axis, the interstellar absorption of X-rays, and distinguishing the contribution of each requires high-quality data and sophisticated statistical analysis. NICER's results for PSR J00, 30-0, 451, and PSR J07, 40-6620, have provided 2 data points on the mass-radius curve. Combined with the GW 170817 tidal deformability measurements and the mass measurements from pulsar timing, the allowed equation of state is being narrowed with increasing precision. Each new measurement is another point. Each point is another constraint. The picture is coming into focus. Pulsar timing arrays have achieved something extraordinary in the last few years. A pulsar timing array is a set of millisecond pulsars distributed across the galaxy, monitored over years to decades using radio telescopes. Because millisecond pulsars are extraordinarily stable rotators, tiny deviations from their expected pulse arrival times can be detected with very high sensitivity. If a gravitational wave passes through the Earth, it stretches space in one direction and compresses it in the other, alternately. This produces a tiny change in the effective path length between the Earth and the pulsar. The combination of this effect and the wave passing through the pulsar itself creates a correlated pattern of timing residuals across different pulsars, correlated in a specific way that depends on the angle between pairs of pulsars on the sky. This correlation pattern is called the Hellings and Downs curve, derived in 1983. In 2023, 4 independent pulsar timing array collaborations announced evidence for this correlated signal at nanohertz frequencies. The North American Nanohertz Observatory for Gravitational Waves, the European Pulsar Timing Array, the Parkes Pulsar Timing Array, the Chinese Pulsar Timing Array. Each independently detected the same background: gravitational waves, with periods measured in years to decades, corresponding to the orbital periods of pairs of supermassive black holes slowly spiraling toward merger, accumulated across the history of galaxy formation over billions of years. And this background was detected using millisecond pulsars as the sensors, using objects born in violence, spinning hundreds of times per second, to listen to the lowest frequency gravitational waves in the universe. There's something almost poetic about it. The most extreme rotation rates of any object in the universe, deployed as ultra-precise clocks, detecting oscillations with periods of years. The cooling history of a neutron star is another observable that probes the interior. A newly born neutron star is extraordinarily hot. 100 billion degrees in the interior, 1 million degrees at the surface. Over time, it cools. The rate at which it cools depends on the physics inside. Specifically, it depends on the dominant cooling mechanism. In ordinary matter, heat is transported and radiated by electrons. In the dense nuclear matter of a neutron star, the dominant coolant is neutrinos. The same particles produced in the original collapse, now produced continuously by various weak interactions in the hot, dense interior. Neutrinos stream out of the interior, carrying heat with them, and the neutron star cools. The dominant neutrino emission process in a neutron star depends on the composition and the phase of the interior matter. In purely hadronic matter, neutrons and protons, the dominant process at high temperatures is called the modified Urca process. 2 neutrons interact, one converting to a proton by emitting an electron and an antineutrino. And then the reverse reaction happens, emitting a neutrino. The net result is neutrino-antineutrino pair emission, carrying away energy. The modified URCA process is relatively slow. A neutron star cooling predominantly via modified Urca would cool gradually, remaining detectable in X-rays for longer. If the neutron star core contain exotic matter, iperon, quark matter, certain superfluid phase faster neutrino emission process become available. The direct Urca process, which requires a higher proton fraction than standard nuclear matter, but which quark matter allows, emits neutrinos far faster. A neutron star cooling via direct URCA would cool much faster. The difference is observable. By measuring the surface temperatures of neutron stars of known age, using the age estimated from the surrounding supernova remnant and comparing them to cooling models, physicists can constrain the cooling mechanism. The neutron star in the Cassiopeia, a supernova remnant, a roughly 350-year-old neutron star. The youngest known in the Milky Way was observed to be cooling faster than expected for simple, modified Urca cooling. The interpretation proposed was that the neutron star had crossed a threshold for neutron superfluidity in the core. When the neutrons form Cooper pairs, the superfluid transition is accompanied by a burst of neutrino emission as the condensation releases energy. This enhanced cooling phase is predicted to last for a period after the superfluid forms. The Cassiopeia, a neutron star, may be cooling rapidly because it's currently undergoing this superfluid formation. If correct, it's the first direct observational evidence for neutron superfluidity, not inferred from pulsar glitches, directly observed in the cooling rate. The maximum mass of a neutron star is one of the most consequential numbers in astrophysics. It divides the population of compact objects into neutron stars below it and black holes above it, and it's determined entirely by the equation of state. Current observations bracket the maximum mass somewhere between 2 and roughly 3 solar masses. The lower bound comes from observed neutron stars. You have to be able to support at least 2 solar masses. The upper bound comes from theoretical arguments about causality. The equation of state can't be so stiff that the speed of sound in nuclear matter exceeds the speed of light, combined with constraints from gravitational wave events. Between 2 and 3 solar masses is a gap. We don't have confirmed objects in that mass range clearly identified as either neutron stars or black holes. But we may have seen one. In August 2019, LIGO and Virgo detected a merger between a black hole of roughly 23 solar masses and an object of roughly 2.6 solar masses. The lighter object might be the most massive neutron star ever detected, at or above the maximum neutron star mass. Or it might be the lightest black hole ever detected, below the lowest expected black hole mass. We don't know which. The mass sits in the gap. This event, called GW 190814, is a reminder that the boundary between neutron stars and black holes isn't a clean known line. It's a region where theoretical understanding is genuinely uncertain, and where observations are now starting to probe. Future gravitational wave detectors will detect more mergers involving objects in this mass range. More data will eventually clarify where the neutron star sequence ends and the black hole sequence begins. The answer will tell us the equation of state. The equation of state will tell us what matter is doing at the center of a neutron star. The Einstein telescope is a proposed third-generation gravitational wave detector planned for construction in Europe. It would operate in an underground triangle of tunnels, each arm 10 kilometers long, to reduce the seismic noise that limits surface-based detectors. At this sensitivity, the Einstein telescope would detect neutron star mergers out to distances of roughly 10 billion light-years. Instead of a few detections per year, it would detect potentially thousands of neutron star mergers per year. Each merger carries information about the equation of state encoded in the tidal deformability and in the post-merger oscillation frequencies. When 2 neutron stars merge, the remnant, if it survives long enough before potentially collapsing to a black hole, oscillates. It rings, like a struck bell, at frequencies determined by its internal structure. These post-merger oscillations produce gravitational waves at kilohertz frequencies between about 1,000 and 4,000 Hz. Current detectors are not sensitive enough to detect these post-merger signals from most events. The Einstein telescope would be. Detecting the post-merger ringing of a neutron star merger remnant would be the equivalent of ringing an atomic nucleus and measuring the note. The frequency tells you the structure. The structure tells you the equation of state. The Cosmic Explorer is the American equivalent of the Einstein telescope, a proposed detector with arms 40 kilometers long, a factor of 5 longer than current LIGO. Together, Einstein telescope and Cosmic Explorer would form a global network capable of detecting and localizing events across most of the observable universe, and extracting the equation of state from hundreds of thousands of mergers combined. The era of gravitational wave astronomy has barely begun. The first generation of detectors established existence. The second generation opened the field. The third generation will transform it. The Square Kilometre Array, a radio telescope network currently being built across South Africa and Australia, with a total collecting area of a square kilometre, will find thousands of new pulsars when it comes online, including, potentially, pulsars near the galactic center, where the stellar density and therefore the neutron star density is highest. A pulsar orbiting very close to Sagittarius A, the supermassive black hole at the center of the Milky Way, would be an extraordinary laboratory. The combination of extreme gravitational field, potential frame dragging from the rotating black hole, and the precision of pulsar timing would allow tests of general relativity in a regime far more extreme than the binary pulsar systems currently available. And if a neutron star were to orbit closely enough to the galactic center black hole to be tidally disrupted, torn apart by differential gravitational forces, the resulting flare of X-ray emission would carry information about the neutron star's internal structure, specifically how easily it deforms under tidal stress. That deformability is again determined by the equation of state. Every new observation is another angle on the same question. There's another extraordinary laboratory for neutron star physics that's closer than you might expect. Nuclear physics experiments on Earth can probe the properties of nuclear matter at densities up to roughly nuclear saturation density, the density of an ordinary atomic nucleus. Experiments at facilities like the Relativistic Heavy Ion Collider at Brookhaven and the Hades spectrometer at GSI in Germany create nuclear matter at elevated densities and temperatures by colliding heavy nuclei. Then study the resulting particle production to infer the equation of state. The PREX experiment at Jefferson Lab used precision electron scattering to measure the neutron skin of lead nuclei, the thin layer of excess neutrons that exists at the surface of heavy nuclei like lead-208. The thickness of the neutron skin is directly connected to the equation of state of nuclear matter at and below nuclear saturation density, specifically to a quantity called the symmetry energy slope parameter. This parameter controls how the energy of nuclear matter changes as you change the ratio of neutrons to protons. It's directly relevant to neutron stars, which are composed almost entirely of neutrons. The PREX measurement came in at a value that suggests the symmetry energy slope is somewhat higher than many models predicted. If correct, it has implications for neutron star radii, suggesting they might be somewhat larger than the softer models predict. But the result was in some tension with other constraints, including the NICER radius measurements. Resolving these tensions is an active area of research. The CREX experiment, using calcium nuclei, provided complementary data. Together, these nuclear physics experiments from a beam of electrons in a laboratory in Virginia are contributing to our understanding of what's inside neutron stars 100 light-years away. The connection between nuclear structure physics and neutron star astrophysics is not incidental. They're studying the same equation of state in different regimes. The nuclear structure, physicists can reach densities up to a little above nuclear saturation. The neutron star astrophysicists can probe what happens above that. The combined picture is more complete than either alone. There are roughly 2,000 known pulsars in the Milky Way. The total number of neutron stars in the galaxy is estimated at around 100 million. Most of them are dark, not beaming radio waves toward Earth, not accreting material from a companion star, not hot enough to be detected in X-rays. They sit in the space between stars, cooling over billions of years. The oldest neutron stars in the galaxy are nearly as old as the galaxy itself. They've been cooling for 12 billion years. A newborn neutron star has a surface temperature of around 1 million degrees. After a few 100,000 years of cooling, it might be down to 100,000 degrees. After millions of years, tens of thousands of degrees. After billions of years, the surface might be cool enough that it's no longer detectable in X-rays at all. A cold, dark, dense sphere of nuclear matter, spinning slowly in the dark between the stars. Nearly impossible to detect, but still there. Still full of superfluid neutrons. Still threaded by superconducting proton flux tubes. Still, perhaps containing quark matter at the center. Still doing physics at its interior that we can't solve exactly. The observable universe contains something like 100 billion galaxies. The number of neutron stars in the observable universe is approximately 10 to the power of 20. 100 billion neutron stars. Each one a sealed archive. Each one doing physics that our best theories approach but don't fully describe. Each one containing matter in states that have no name in ordinary chemistry. The way matter organizes itself under extreme conditions has occupied some of the sharpest minds in physics for a century. The search for phase transitions, abrupt changes in the properties of matter at particular combinations of temperature and density, is one of the central themes of condensed matter physics, nuclear physics, simultaneously. Water changes from solid to liquid to gas. Helium becomes a superfluid. Electrons in certain materials form Cooper pairs and become superconductors. Iron loses its magnetic order above a certain temperature. All of these are phase transitions. The underlying matter is the same. The organization is different. The properties change abruptly at the transition, not gradually. Inside a neutron star, the question is, are there phase transitions? The answer is almost certainly yes, but where they occur, what separates them, and what the phases on either side look like are open questions. The transition from ordinary nuclear matter to a superfluid state is itself a phase transition. The possible transition from hadronic matter to quark matter is another. The possible appearance of hyperons constitutes a change in phase in a broader sense. And within quark matter itself, there may be multiple phase transitions between different color superconducting phases. The question of whether these transitions are first-order, discontinuous, with a sudden jump in density at the transition, or second-order smooth, with the density changing continuously, has consequences for both the internal structure and the gravitational wave signal of neutron stars. A first-order phase transition in the interior of a neutron star would create a sharp interface between two phases. A conversion front between nuclear matter and quark matter would sit at a particular depth inside the star, defined by the transition pressure. Objects with masses just above and below the transition mass would have different internal structures. Their mass-radius curves would show a feature, a kink, a ledge, or even a gap at the transition mass. Detailed enough measurements of many neutron star masses and radii would reveal this feature, or its absence. The measurement campaign of the next generation, using Einstein telescope and Cosmic Explorer to accumulate thousands of mass-radius points, will be sensitive to such features. A gap or kink in the observed mass-radius distribution would be direct evidence for a phase transition inside neutron stars, one of the cleanest possible signals of exotic matter. Something happens when you step back from all of this and look at what neutron stars are actually telling us. They're telling us that our picture of matter is incomplete, not wrong, not inaccurate at the scales where we've tested it, but genuinely, demonstrably incomplete when you push far enough. The Standard Model of particle physics is the most successful physical theory ever constructed. It describes the electromagnetic, weak, and strong nuclear forces. It predicts the properties of all known fundamental particles with extraordinary precision. But the Standard Model doesn't tell us what QCD does at high baryon density. The equations exist. The interactions exist. The particles exist. But the mathematics resists exact solution in the regime that matters for neutron stars. We have a complete theory of the relevant physics, and we still don't know what it predicts in the regime of cold, dense matter. That is a remarkable situation. In most areas of physics, the problem is that we don't yet have the right theory. For neutron stars, we might have the right theory, but lack the computational tools to solve it. Every advance in quantum computing, every advance in lattice QCD, the numerical technique for solving QCD on a computational grid, is also a step toward understanding what's at the center of a neutron star. The tools of condensed matter physics, particle physics, nuclear physics, gravitational wave astronomy, and X-ray astronomy are all converging on the same object, all trying to decode the same message. And the message is, here is what matter looks like when you've taken everything ordinary away from it. Here is what's left when you strip away the empty space in atoms, when you annihilate the individual identities of protons and electrons, when you crush nuclei until their quarks are almost free and the vacuum itself becomes unstable. Here is physics at its limit. And the fact that we're closing in on the answer that the combination of gravitational waves, X-ray observations, pulsar timing, and nuclear physics theory is genuinely narrowing the possibilities, is one of the most exciting developments in physics of the last decade. There's a concept in neutron star physics called the equation of state. We've used the term many times. It deserves a moment of clear explanation. An equation of state is a mathematical relationship between the thermodynamic properties of a material, its pressure, density, temperature, and composition. For most ordinary materials, we know the equation of state well. For an ideal gas, its pressure equals density times temperature times a constant. For water, it's more complex but thoroughly characterized. For steel, for concrete, for every material we use in engineering, we know exactly how it behaves under any conditions we'd encounter. For neutron star matter, we don't. The equation of state determines almost everything about a neutron star. Given the equation of state, you can calculate the mass-radius relationship, how the mass and radius of a neutron star are related for all possible central densities. If you plot mass against radius for all possible neutron stars, you get a curve. Different equations of state give different curves. A stiff equation of state matter that resists compression gives a curve that extends to higher masses and larger radii. A soft equation of state gives a curve with lower maximum masses and smaller radii. The curves are different, distinctly different. And we can measure where individual neutron stars sit on the mass-radius plane. Nicer mass-radius measurements give individual points. Gravitational wave tidal deformability measurements give constraints on the curve's shape. Pulsar mass measurements from timing give constraints on the maximum mass. Nuclear physics experiments on Earth give constraints on the equation of state near nuclear saturation density. All of these constraints together are converging on the actual equation of state. Not a single line. A band of allowed curves, narrowing with each new measurement. The picture that has emerged so far is roughly this. Neutron star matter at nuclear saturation density is moderately stiff, stiffer than many early models predicted. It stiffens further at a few times nuclear density. Then, at some density that might be 3 or 4 times nuclear saturation, something might happen, a phase transition to quark matter, which could soften the equation of state suddenly, or a more gradual crossover. That transition region is the frontier. That's where the exotic matter lives, if it lives anywhere. That's what every new observation is trying to constrain. And then there's what it all means. Not technically, philosophically. Ordinary matter, atoms, molecules, the periodic table, chemistry, biology, everything we interact with exists in a particular regime. A regime of moderate temperatures, moderate densities, moderate electromagnetic fields. In this regime, the universe arranges itself into atoms, which bond into molecules, which assemble into structures, which give rise to complexity of staggering variety. But that regime is narrow. The vast majority of the mass of the universe exists in conditions far outside it, in stars, in supernova remnants, in neutron stars, in the plasma around black holes. The regime where atoms exist, where chemistry works, where we live, is a thin slice of all possible conditions. A neutron star shows you what's on the other side of that slice. It shows you matter, stripped of the organized complexity we live in, compressed down to something more fundamental. A neutron star is matter simplified. All the complexity of chemistry, all the structure of atoms, all the hierarchy of molecules, stripped away. What's left is quantum mechanics and gravity, grinding against each other at the smallest accessible scales and the largest forces in the universe, simultaneously. And in a strange way, neutron stars are deeply personal, not in a comforting sense, in a literal, chemical sense. The atoms in your body were made in stars. The heavier ones, the iron in your hemoglobin, the calcium in your bones, the iodine in your thyroid, the gold in anything you own, were scattered into space by supernovae and neutron star mergers. The event that creates a neutron star is also the event that distributed much of the chemistry of complex life through the galaxy. The strontium detected in the spectrum of GW 170817. The gold estimated to be present in the kilonova. All of it eventually incorporated into gas clouds, then molecular clouds, then star-forming regions, then planetary systems. Then, in at least one case we know of, onto a rocky planet in a habitable zone. Then, into living things. The iron in your blood was forged in the core of a star that went supernova billions of years ago. The gold, in any ring you own, was made in a neutron star merger. You exist because neutron stars formed. There is something almost paradoxical about this. The most extreme, the most alien, the most incomprehensible objects in the universe, the places where matter ceases to exist in any familiar form, are part of why matter like us exists at all. The violence that produces a neutron star is the same violence that seeds the galaxy with the raw materials for chemistry, for planets, for biology, for the particular arrangement of atoms that can look back at the source and wonder what's happening inside it. We don't know with certainty what's at the center of a neutron star. The measurements are narrowing the possibilities. The observations are accumulating. The theoretical framework is maturing. But the definitive answer, what phase of matter occupies the inner core, at 5 or 10 times nuclear density, whether quarks flow freely or pair up or crystallize, whether strange quark matter is involved, that answer is still ahead of us. Not infinitely far ahead. The next generation of instruments will produce transformative constraints. The combination of gravitational wave detections from Einstein Telescope and Cosmic Explorer, X-ray measurements from successors to NICA, pulsar timing from the Square Kilometre Array, and nuclear physics experiments on Earth may, within the next few decades, narrow the equation of state to a band narrow enough to answer these questions with confidence. Whether the inner core is purely hadronic matter, neutrons and protons and their heavy cousins held up by quantum mechanical repulsion, or quark matter in one of its predicted phases, or strange quark matter, or something else entirely that the theory hasn't yet captured. The history of physics is full of surprises at the boundary of what's known. Every time humanity has probed matter at a new scale, new phenomena have appeared. The structure of atoms was a surprise. The nucleus was a surprise. Quarks were a surprise. The quark-gluon plasma turned out to be a nearly perfect fluid when the expectation was a gas. The inside of a neutron star might hold another surprise, something the equations hint at but don't quite capture. Something that, when we finally constrain it well enough to see it, will require revising our understanding of what matter fundamentally is. That's not a failure. That's exactly what science is for. Standing at the edge of what is known, holding tools just barely good enough to see something at the limit, and reaching anyway. When you look up tonight, if the sky is clear, if you find a dark spot, if you let your eyes adjust, you might be looking toward the plane of the Milky Way. Along that faint smear of light, somewhere in the dark between the visible stars, there are 100 million neutron stars cooling, spinning, doing physics we haven't solved. Spinning hundreds of times per second, or barely at all. Sometimes glitching. Sometimes flaring. Sometimes spiraling toward a partner across millions of years, until the final plunge, the collision, the burst of gravitational waves, the spray of gold. They don't announce themselves to the naked eye. They exist quietly, in the dark, holding the answer to the question of what matter is at the deepest level we can currently probe, in a form we are slowly, carefully, precisely learning to read. One merger, one glitch, one pulse profile, one mass measurement at a time. The answer is in there. We just have to keep listening. Good night.